All right, guys. I'm just having a look here. Yeah, we'll be able to see when people log on. Join. Yeah, there's nobody yet, nobody at the moment, but there is 2 minutes to go until 11. So we'll see. There's one person who's joined. Welcome. So we'll do a quick announcement at 11. So I just want to share this, the paper that we're doing. Yeah, where should we starting? So we're starting with the KZN September 2025. Now, the paper 2, just to review the paper that the guys that wrote the government exams did. So last week, it was last week Monday. It's like a pretty standard sketch there for 500. Yeah, with a bit of reduction. This is a pretty standard question overall. It's got quite a lot of compound angles. There's a bit of double angles there in 5.1.3. Yeah. Question 5.2 and 5.3 both have compound angles in them. And the guys always get stuck with that. So that's one where you have to like contract it, bring it in, reduction, contract it. And then over here, this is one like in the module, there's 3 theta, yeah, where you need to say 5 theta minus 2 theta and 5 theta plus 2 theta. Yeah, you get like both things equal that. Mm-hmm. Yeah. And then we've got another one here, which is it's like this. Yeah. So theta is obviously a third of 157.5. Yes, and no, well, actually, it's a seventh of it. It ends up being 22.5. There's reduction involved there. Because look how you see this one's more than that one. So how can 3 theta be more than 5 theta if it wasn't reduced? No, they're the wrong way around. You swap them around. So really? That yeah, look at that. Because it's yeah. So theta is actually a third of 67.5, which is 22.5. So why would they swap? Come on. Yeah, that the first thing you do is apply that density. But yeah, I think we're going to get to it now. We got only got over here, but it's fine. Yeah, we can do this. So yeah, basically what we'll do here is we'll just share the screen when we're talking about the question, and then we go on to the working of it, where we'll just we'll start sharing this screen so they can just see the board. So we'll view. I think next time the stream is off, I'll be able to get it so we can have the paper there, like small pins with a lot of orders view, but it's cool. Yeah, I think I'm just going to start working through. So, welcome guys to the 2025 trick revision, and we are starting with paper 2 today because we want to start with the subject that more people do. So, physics is the case in physics paper is tomorrow, but guys have already written maths paper 2. So we're going to start by working through the maths paper 2. And I'm going to start with the trig because it seems to be everyone's biggest lead area in maths. So, truly that's everyone's favorite section. I just wanted to say before we start, this is AJ. He's a maths and physics tutor for AJ Maths and Physics tuition. He's been at school going on 10 years now, right? And I'm his brother, Larry, also a maths and physics tutor. I haven't been doing quite as long as AJ, but I've been at this for as long as we can get more of it, almost as long. So welcome everybody, and I hope that you benefit from assistance to that. Yeah. So we'll jump right into it. Some of the things about the live stream as well, we want people to ask questions. So for the headline guys, if you are logged on, then what you can do is you can send through questions on the WhatsApp line, and we'll those ones first. And then if other guys want to submit questions in the chat, then we'll do that with the 30 minutes like Q&A session at the end. So we're going to be pretty much teaching, working through problems for you for the first 2 hours, and for the last 30 minutes we'll be taking submissions and Q&A. So it's the working through of the example is. Okay, so maybe it starts with that. The first question that we're looking at there is given cos of 16 equals k, cos of 16 equals k. Now, the first thing in the trig questions, in question 5, is normally going to be a diagram question, and this is a diagram question as well. It's the lesser known diagram question. So you guys would probably be used to seeing diagram questions where you need to draw the Cartesian plane, and we'll talk a little bit about that at the end of this question as well before we move on. But in this question, we don't have an unknown angle. We know that the angle is 16 degrees. What we don't know is we don't know the ratio. So we're going to be working in terms of this unknown ratio k. And the first thing to do is to write it as a ratio. So we know that all numbers can be written over 1, right, without changing them. So we can say that cos 16 is equal to k over 1. And then from there, we need to draw a diagram. Now, from our definitions, right, and if you battle with definitions, you'll need to go back to the grade 10 stuff and start right from the beginning. From our definitions, we know that cos of 16 is equal to k over 1. So if this is 16 degrees at the bottom, then the adjacent will be k, and the hypotenuse will be 1, adjacent over hypotenuse. Cos is adjacent over hypotenuse. Then we can use Pythagoras to find the missing side, the opposite, and you can label it O if you want to, right? And we'll say that O squared is equal to 1 squared minus k squared. And that is just going to be 1 minus k squared. Then we have square root, right, to get O on its own. So it's the square root of 1 minus k squared. And we might as well write that in at the top there. Root 1 minus k squared. Yeah. So that's going to help us now, because in order to fill in ratios of sine or tan, we're going to need to know what that opposite is, right? And notice I just jumped right into that before even looking at the first question, because most of the time we're going to need that working. So you should be careful. If they only require you to do it in question 2, then you don't want to do it too early, but we'll see we do have to do it right away. So for 5.1.1, they ask us to find the sine of 344. Okay. And once we've got the triangle, then all we have to do is reduce this to some kind of angle of 16. So you want to be looking for reduction. 360 minus 16 is what we've got here. Sine of 360 minus 16 degrees. That's equal to 344. And because 360 minus theta is in quadrant 4, we know that from our cast diagram that sine is not positive in that quadrant. So for an angle of 344 degrees, sine is going to be giving us a negative answer. That's what that means. And in fact, the answer will be negative sine of 16. So this is reduction, right? If you need to revise reduction, then you should probably start with the grade 11 stuff and work on your reduction rules, right? That's where we first see reduction in the middle of grade 11 trig. So we will look at how to take these angles and break them down, right? And now we can see that we've got sine of 16. So for all of the ratios, sine, cos, and tan of 16, we can fill them in using this diagram, because that's a triangle with 16 degrees in it. So sine is opposite over hypotenuse, and that's going to be that over that. So the sine of 16 is going to be root 1 minus k squared over 1, but we mustn't forget about that minus, that negative sign in front there. Root 1 minus k squared over 1, and that will just simplify to negative root 1 minus k squared. Okay, and that's it. That is the answer for 5.1.1. They normally will include some working marks here for the triangle and everything. So try and include that. Try and include all of this working under the heading of 5.1.1. And the next thing we want to do is take a look at some of the other ones. 5.1.2, we've got tan of 106. So this is quite an interesting one, actually quite uncommon. Tan of 106 is, it can be written as tan of 90 plus 16. You want to try and look for
the 16, and then generally we try to stay away from 90 plus and 90 minus unless we have to, but here that's going to be the easiest way to go. And then we've got tan of 90 plus. So if you remember, those are co-ratios, right? Our co-ratios look like this. Sine of 90 minus theta is equal to cos of theta. Cos of 90 minus theta is equal to sine of theta. And then sine of 90 plus is cos theta. Cos of 90 plus is negative sine theta. So don't forget about those two. The sine of 90 plus and cos of 90 plus. So this last one is negative, and we must remember that. And that's because in quadrant 2, cos is negative. But this one is not negative. Sine of 90 plus theta. So notice we actually don't have co-ratios for tan, and that's why I say this one's uncommon, because we're going to have to break it down into sine of 90 plus 16 over cos of 90 plus 16, and then we'll have to fill in those ratios separately. And then we use, well, we're going to use reduction first. So sine of 90 plus, we said, was just positive cos. And cos of 90 plus will be negative sine. Fill in that again. You must get rid of the 90 plus, right? And we're working with 16, not theta. 16. Okay. So now we've got cos 16, we've got sine 16. We can fill them in using those ratios. So cos of 16, we said was k, right? So we can just fill that in as k. And then on the bottom, sine of 16 is root 1 minus k squared over 1. So just root 1 minus k squared. And then there's a negative in front, right? So that negative in front of the sine 16, you can just pull it out, right? And write it in the front. It's the more conventional way to write it. In the front or on the top is fine, but try not to leave it at the bottom. One thing that you'll find as well is that you can fill these in as ratios, like write them as k over 1 and write them as root 1 minus k squared over 1, but then you end up with like a double fraction, and you can just avoid that by doing a little bit of simplification first of all then. Okay, and then lastly, we've got the dreaded one. 5.1.3 involves a half angle. So when I teach this, I distinguish between the double angles and the half angle, because the half angles are more difficult to do. So if you've got a double angle, like if it was cos of 32, that would be easier to do because you can expand it straight away. But with the half angle, what you want to do is you want to kind of start with the normal angle and then break it down. So if we've got cos of 8, if we're looking for cos of 8, how do we start that? Well, we should actually just start by writing down cos of 16. Okay. And we're going to say that cos of 16 is equal to 2 cos squared of 8 minus 1. So we use the double angle formula on the 16, right? Rather than with the other one, you would start with the 32 and then you would break it down into 16s. So that's the way to go here. Now we also need to make this equal to k in some way. So we actually want to start with an equation, not just an expression. Cos of 16 is equal to k, right? So that means 2 cos squared 8 minus 1 is also equal to k. So we write down an equation, and then we're going to start working our way down to cos of 8. So we bring the 1 over, first of all. Keep the 2 there. We get k plus 1, and then we divide by 2. And then we have the square root. So we have cos squared of 8 is equal to the square root of k plus 1 over 2. So nice and easy here if you get started correctly, right? If you start with the expression of the normal angle and then treat it as the double angle, then it works out fine. But if you try and start with like the cos of 8, you'll get very stuck. Okay. 5.2. 5.2. Okay, let's have another look at this paper for the guys that are just joining now. The graphs.
Cool.
Yeah.
You'll find that you've got a lot to say about it. So, yeah, I just want to share the paper. So, just for the guys that are just starting out, you can find the paper on stanmorephysics.com as well, and it is Degree 5 Maths Paper 2. Right. So 5.2, you can see is just a normal reduction question there. And well, there's one thing that you need to watch out for here. I'm always telling guys to watch out for these compound angle contractions, right? So an expansion is where we take the compound angle and we write it out. And most guys don't battle with that. If you got guys of like a plus b, most guys can write that out. But when you see the expanded form, trying to write it back in the contracted form, a lot of guys will just miss that and not see that they have to do that. They start expanding again, and it's a mess. So let's go back to this. Okay.
All right. You're going to erase 5.1. If you guys are taking down notes, then don't stress. This also will be uploaded afterwards, so you can go back to it and re-watch through it. So don't worry if you miss something.
You can come back and find it later. Okay. So what we were looking at there was
Cos squared of 180 plus x.
And yeah, cos squared of 180 plus x.
And then we've got a square bracket there with a couple of brackets inside of it. So tan of 360 minus x, cos of 90 plus x, and sine of x minus 90. And then lastly, cos of 180.
Okay, so this is probably not going to end up being
a compound angle contraction because of that cos 180 on the end. But anyway, let's just see how it goes. So a good thing to remember when you're looking at reduction is that the squares will always be positive, right? The squares will always be positive. So even though on our cast diagram, right, we need to remember which quadrants are positive and negative. Cos of 180 plus, right? 180 plus is in quadrant 3, so cos is negative there. But this is actually two coses side by side. So it's cos of 180 plus x times cos of 180 plus x. And if both of these become negative, right, the negatives are going to cancel out. So it's going to become positive. And you really want to make a good mental note of that. Remember, you'll see these things over and over again. The question is, are you going to remember how to tackle them next time? So if you've got a square, even if it's in a negative quadrant, it's going to work out to positive. It's going to be cos squared of x, right? Cos of x times cos of x. And then simplifying here, we've got tan of 360 minus x. 360 minus, tan is negative there, negative tan of x. Cos of 90 plus, we said that that was negative sine of x, right? And I like to write these in brackets. It's good to write them in brackets because you don't want to make a mistake and think that you're adding and subtracting them. This is all one term, so it's good to have these in brackets. You can put both of them in brackets. Sine of x minus 90. This one is actually a little bit of a tough one, the x minus 90. Now, there's a couple of different ways to deal with that. If you've got x minus 90, right, remember, it's not the same thing as 90 minus x. Okay, so how do we deal with that then? It's not the same thing as 90 minus x. There's two ways that you can deal with this. You can add 360, but then you end up getting 270, and 270 is not good. So I'd say the only real way to deal with this is by pulling out a negative inside the bracket. So we'll have sine of negative 90 minus x. And a lot of guys will just say, you know, you'll find that these questions, people skim over them. So in some cases, people will just say, oh, that's negative sine of x. and then or negative sine of 90 minus x, and that is true in this case. See, sine of a negative angle will be negative sine of x. But if this was cos of negative 90 minus x, then cos of a negative angle is positive, right? Cos of a negative angle is positive. So yeah, just be careful, make sure you do the factorization first. And that's going to end up being negative cos of x. Okay, so we are going to need to do that here at the top, unfortunately, as part of our working. So this is sine of negative 90 minus x and cos of 180, right? Cos of 180. Then the cos of 180 you can actually evaluate, right? Cos of 180 has a value of -1. But just a tip, if you are battling to remember the special angles or any of the angles, just use your calculator. So I've noticed a couple of guys still need that advice, right? You can use the calculator to remind you. If you get stuck, then you might as well use your calculator. Nobody's going to know. If you get enough practice, then you will memorize them eventually. Okay, so we got a -1 there. And we're getting close now. So we got cos squared x. Negative times negative is going to be positive tan x sine x. Right? And then over here we've got sine of 90 minus x. Sine of negative 90 minus x, it's going to become negative sine. And then it becomes negative cos. Times -1. And yeah, so we get, again, we just need to multiply these two. We've got cos squared of x, tan of x, sine of x, plus cos of x. Okay, and now to simplify this, we will need to write this. We'll need to bring these two terms together over a common denominator. And so we will want to write this, the tan as sine over cos, right? Sine x over cos x. And this is cos x over 1. We can multiply by cos x on the top, multiply by cos x on the bottom, and we'll have cos squared x over cos x. Now when we multiply these together, we'll have sine squared x plus cos squared x. So sine x times sine x is sine squared. And this is all over cos x. So once you've got that common denominator, you can bring the two numerators together over that single common denominator. Okay, lastly, sine squared plus cos squared, that's an identity, right? Grade 11 identity gives us 1 over cos x. And cos squared x, we've got that in the front there. So one of these coses will cancel with that cos on the bottom, and we're left with cos x as our final answer. Now the instruction here was write this as a single trigonometric ratio. So we have to have one single trig ratio. It could be cos x, 1 over sine x, or something like that. So we have completed the task that we were asked to do there. We've taken lots of terms and brought them together into one term. Okay, now some things that you want to pay attention to here, if you're getting stuck with the basic reduction, like if you're getting stuck with some of the basic reduction, you want to make sure that you go back and go through the reduction, right? Okay, things like which quadrants are positive, which quadrants are negative, the co-ratios, and then yeah, those types of things. We want to make sure that we get some practice with those fundamentals first. But actually, I find that most guys they don't battle as much with the reduction and the identities. They normally battle with algebra, specifically the algebra of fractions, right? So things like bringing multiple terms together into one. That's always going to happen with these questions, right? If we're trying to end up with one term, we need to take lots of terms and bring them together into one term. So over here, we start off with a bunch of terms, and we need to bring them together into one term. Once you've brought them together, then you've got a chance at cancelling some things out, right? So bringing many terms into one term, that should be the general flow of the problem. Unless you're looking at some more challenging examples, you will see some where you need to bring something in, but generally speaking, you're going to be bringing things together and cancelling them out. It's very rare where you have to bring something in, like if you have to split up a 1 into a cos, that type of thing. Those we'll take a look at a broader variety of the types of questions that you will see. But these are the main things that you want to focus on for the fundamentals. Then for guys that are sort of in the mid-range, I would say make sure you don't neglect the compound angle identities. Like try and go through a lot of past papers that have compound angle identities in it, especially the ones where you need to bring them together, because over and over again, I see guys getting stuck on those, guys that otherwise should be getting 60s and 70s, and then they get like 40 for this part. So I can't stress that enough. The compound angle identities. A good thing to do is to use the Mind Action Series textbook and look at the different sub questions in that textbook. So what you can do is go through an exercise on it, like for each of the days that you've got planned out. If you're doing some past papers, that's great. But then also try and work in an exercise from the textbook to work on your fundamentals and to work on multiple questions at the same time. Because what you'll find is that going through past papers, you go through one question of each time, and then you move on. And by the time you come back around to it, you've forgotten how to do that. So most of the time, to build for proper skill building, you want to do like a full set of 5 to 8 questions of that particular type before you move on. Okay. 5.3, so we're getting closer to the end now. Looking at that, we're more than halfway through the marks here. We've got 13 marks to go for this question. Quickly on the reduction as well, it's good to note that, if you want to remember the shortcuts or the reduction formula for each quadrant, we've got theta 180 minus theta 180 plus theta and 360 minus theta. If you ever see a negative theta, right, that's in quadrant 4, because a positive angle goes up into quadrant 1. So a negative angle goes down to quadrant 4. You can also see that if you add 360 there, which we're always allowed to do, you end up getting the same thing, 360 minus theta, right? 360 plus theta, or theta plus 360 are both in quadrant 1. You can write them in either order, right, as long as they're both positive. And then one thing to remember here as well is that theta minus 180, if you see this one, that's actually in quadrant 3. Right? So if you start with an angle in quadrant 1, theta, and you swing back 180 degrees, you'll end up in quadrant 3. So that's the geometric way to remember that. But you can also add 360 and you get theta plus 180, which is the same thing as 180 plus theta. So you don't have to show that simplification in grade 12. In grade 11, you do have to show that simplification. But in grade 12, you can just, whenever you see, like for example, tan of 180, of theta minus 180, it's going to just be tan theta. But cos and sine of theta minus 180, well, they'll be negative, right? Because only tan is positive in quadrant 3. Okay. All right, so the next one is a compound angle identity question. And I'll write it on the board here. It is given cos of 3 theta plus cos of 7 theta over cos of 5 theta is equal to 2 cos of 2 theta. Prove the given identity. Okay, so looking at this, you'll probably see the cos of 2 theta and think that this is a double angle question, but it's actually a compound angle question, and it's quite a difficult one to get if you're not used to this format. So this is the type of question format that you should learn, right? When you see something like this, cos of 3 theta, cos of 7 theta, what we want to try and do is rewrite each of them as a compound angle expansion where you've got the same angles. So let me just show you what that means. So in this case, cos of 3 theta can be written as 5 theta minus 2 theta, right? And the reason we would want to write it like that is because on the other side, we can write the 7 theta as 5 theta plus 2 theta. Now, why would we want to do that? that's the question, right? That's why I say this is a type of question you have to learn the format of, because, well, we've got cos of 5 theta on the bottom. That might help us a little bit, but what's going to happen here is when we expand this, we're going to have terms that will cancel out because of the identical angles. So let's see. I see that somebody's trying to call me while I'm in the middle of the live stream, so that's not going to work. But anyway, we've got cos of 5 theta minus 2 theta, cos of 5 theta plus 2 theta. Let's see, just looking. Okay, I'll check it out now. We want to expand these. Okay, but my phone's low, I'm trying. It's okay. I see, because of the fact that the link is broken, people are not finding it. But it's you know, yeah, I think if you can just there's WhatsApp on that PC there. Maybe. Okay. Did you send it? Yeah, I did, and I also posted it on Facebook and Instagram. But you know, like, yeah. So next week's one will probably work better. But anyway, okay. So luckily this will be uploaded anyway, so it's not really a problem. But we want to prove the identity. So first of all, we want to only work on one side. We're going to work on the left-hand side, and we're going to simplify the left-hand side. So we said that we've got this compound angle expansion, and then what's going to happen from here is we are going to break this down into using the compound angle formulae. So it will be cos of 5 theta sine of 5 theta plus sine of 5 theta cos of 5 theta. Let's see if you have a simple instance. Plus cos of it's posted on the status 5 theta cos of, sorry, this should be sine. You can distract that's okay. It's not your plus 2 theta minus sine of 5 theta sine of 2 theta. Okay, and then these two terms, you'll see they'll be identical, so they cancel. Sine of 5 theta, sine of 2 theta. One's positive, one's negative. Right? All of this is over cos of 5 theta, and then we're just going to leave that there for now. Now, what we've got here is another pair of identical terms, but they are going to add up, right? So because they're both positive, it's like x plus x. We've got two of them, 2 cos of 5 theta cos of 2 theta over cos of 5 theta. And the cos of 5 theta will cancel, and that leaves us with 2 cos of 2 theta. Okay. Cool. Yes, that is the end of that one. So you can see now that it's equal to the right-hand side, but it's good to write down equals the right-hand side. The cos of 5 thetas cancel out. We've still got a couple more questions to go to get to the end of question 5. So just a reminder, this is KZN September 2025. You can find it on stanmorephysics.com. And yeah, now I am going to move on to 5.3.2. This is 5.3.1. With 5.3.2, you want to notice there that it says hence. So it says hence determine the value of cos of 157.5 plus cos of 67.5 over cos of 112.5. Okay. Hence determine the value without the use of a calculator. So there's two things here. We're probably going to end up with special angles because we need to evaluate, right? The other thing is that we've also got something which roughly fits the format of the original identity. So when you've got a question that says hence, you want to apply that identity that you've just worked through. So we want to go from this form to that form. Now, looking at this, we've got cos of 157.5, cos of 67.5, cos of 112.5. These three angles are all multiples of something, right? And we want to find out what that is. But also, notice we've got a small angle, we've got a big angle, and we've got a middle angle. And that's the same thing, a median angle. And we've got the same thing here in our identity. 3 theta is small, 7 theta is bigger, 5 theta is in the middle. So this is roughly fitting the format, but these two are the wrong way around. So we want to try and take these and divide to see what theta should be in this example. And if we take 67.5, which is the smaller angle, and divide by 3, we get 22.5, right? So this is cos of 3 times 22.5. This is cos of 5 times 22.5. And this is cos of 7 times 22.5. Now, what happens there is, like you can see that fits the format that theta, in this case, is 22.5. Now, whenever you see a 22.5, you should be thinking of 45, right? Because that's the special angle. Now, obviously, 2 times 22.5 would give you 45, and that is an angle that we can evaluate because it's a special angle. So if we look at this identity right there, we've got a 2 theta, which is going to give us 45. So the correct application of this identity is to say that that is going to give us 2 cos of 2 theta. And theta, we said, is 22.5. And there's no real way to work that out besides inspection, right? You just got to look at this and see that it fits the same pattern as that. But remember, when you see a question that says hence, that's likely going to be what you need to do. You need to use that identity that you just worked out. And that's 2 cos of 45. Cos of 45 is root 2 over 2. It doesn't matter if you use root 2 over 2 or 1 over root 2. In the finals or in grade 12 in general, I would recommend using root 2 over 2. Okay, that's something that I see quite a lot. Don't do that, guys. Don't leave the cos there and just replace the angle, right? Because cos of 45, the whole thing must give you that ratio. So the whole thing must be replaced with root 2 over 2. Okay, and that's going to give you root 2. Okay, so root 2 is our final answer for that one. And then we've just got the general solution. Just the general solution. I'll do that one. Yeah, that's cool. So Murray's going to take over for the general solution, guys.
As you're done in a trade now for these couple of minutes.
Yeah, I hope all the extra advice was helpful as well. We'll try and do quite a bit of that as we go through the different questions, and then also, in the condensed notes and throughout the rest of the sessions, we'll make sure to make a note of the different types of problems you need to do. So I'll hand over to Murray.
All right. So what we're dealing with in 5.4 is a general solution that is a quadratic trig equation. So because of the way that it's written out, I'm sure you guys are aware algebraically of what some of you will be aware of what a zero product is. That is basically the form that we want anything that we're factorizing to be in before we start solving. So let's take it back a moment here, to the fundamentals. Like, let's say we had, if we were back in grade 9 and we had something like x squared minus 5x, right? Plus 6 equals 0. So what we would want to do, given an equation like this, is we first want to factorize it. But what's important to keep in mind when you factorize something like this, we want factors of that c value that add up to this b value here. So we're basically going to have x in both brackets, and we're going to have a minus 6 plus 1. Now, here's the important bit, is that it's actually got to be equal to 0. Now, I see a lot of learners from grade 10 to 12, more or less, that will try to solve when there's still something on this side. Like let's say we have a value on that side, right? But that's not what we're going to worry about, because that zero product is essentially called that because you've got the product of two brackets equal to zero, which means that we can get to solving once it's in that form. Just like we would here, we would say, x equals -1 or x equals 6. What we're going to find in this case is because of the form that it's in, we don't actually have to do much simplification. So I think I'll keep this here just as a reference so that everyone's aware of why we can take those two brackets that we've got and we can say, 4 sine 3x. Let's start with that. We've got 4 sine 3x plus 1. And put another bracket here, which is sine x minus 5 cos x. And then that's equal to 0. Now, I did kind of run out of space there, but that equals 0 is what I was talking about here. The idea is that because those two brackets have a product equal to 0, we can, just like we would here, you see the logic is we don't just change the sign. The idea is that we change the sign here, but actually what we're saying is what I would want to sub into this bracket in order to get a 0 is I would sub in a -1. I get -1 plus 1, that would give me a 0. In this case, I would get a +6 minus 6, that would give me a 0. That's why we end up with two solutions for that. Now with this, we're going to essentially do the same thing. We're going to say that 4 sine 3x is equal to -1, right? Just like how we said x was equal to -1 there. And then that's a trig equation that we'll work with in a moment. Over here, we'll have that sine x is equal to, changing the sign again, 5 cos x. Now, taking those two solutions out of the brackets means that we can get to work with these two trig equations that we have. Essentially, it's turned into 2, and we're going to need to see how far we get with each. Sometimes these equations will become invalidated. Sometimes they'll have real solutions. We just have to see what we end up with. So looking at, let's start with the one on the right. What we're going to do is we're going to keep in mind that we've got a sine on the left and a cos on the right. Now, the guys who know their stuff will already be thinking in terms of identities, right? Because we've got an identity that goes back to the beginning of grade 11, which is the quotient identity. Sine x. See, I'm going to divide both sides by cos x. And then that'll cancel that cos on the right. And sine x over cos x, I'm sure you guys are more or less aware that it is tan x equals 5. Now that's valid because tan, if we look at the graph of tan here, I'll just do a quick one of it. Let's take a look, right? Tan has a range that isn't limited, it's not restricted to certain values, right? It can go to all the values of y. So if this was sine or cos, right? Now sine and cos are limited to +1, -1 on the range. That's what the range is for sine. But tan x equals 5 is a perfectly valid solution, so we can get to solve it. Let's pursue this equation right to the end, and then what we'll do is take a look at that one and see if we get valid solutions out of it. So let me try this one out here. I'll say shift tan 5, and what I find is the value associated with 5, which would look something like this. You have a 5 over here, and what you'd have is the acute angle 78.69. That's what my calculator's given me. So shift tan 5 gave me x equals 78.69. Now, I may be rushing ahead there to say that x is equal to that, right? Because we have a number of ways of referring to it depending on what your teacher says. Your teacher might say key angle, your teacher might say reference angle, right? But because we're using a method known as the QRS method to solve this general solution, we need to, I'm going to go with ref, right? You can call it the key angle if that's what your teacher calls it. It's really up to you. Now, the reference angle is that acute angle that we find when we solve that trig equation, shift tan of 5. And then what we'll need to keep in mind is that tan is a periodic function, right? If I continue this axis out here, we've got our first asymptote at 90. And we've got a, if you like, put another tan curve there, another x-intercept. And now these are really important to know. Like 90 degrees there for that asymptote, you know, we repeat that value of 0 here every 180 degrees. So what is that? That's the period of tan, right? And I'm not going to go into too much detail about that, but if you guys don't understand this, then you need to take it back to the grade 10 trig, the trig graphs, because I'll tell you something. When it comes to understanding your equations, it really helps a lot to know about your graphs, because now your matrix, you've learned everything that you need to know for the finals. You sort of tie them back together. You might learn the algebraic trig before you learn the graph, but you take a lot from the graph and apply it into the algebra. It's really a helpful thing to work that way. Now, because we know this is a periodic function that repeats every 180 degrees, what we're going to start doing at this point is we're going to solve for tan. Now, there's quite a lot to say about how we solve a general solution for tan. For sine and cos, we'd have two quadrant solutions. And I'm going to sort of talk about that a bit here. Because if I draw the standard sine graph here, let's see, standard sine graph starts at 0, so it's going to look something like this. Right? What we can see is, let's say we had a set value. Now, 5 wouldn't work, like we said, but let's say we had a set value that is less than 1 and greater than 0. Look at those solutions, right? Look at how they're oriented on the graph. You've got two solutions that are close together, and then one that would be further away. If I extend that one a bit, I should do that. Extend that one a bit, and you've got another solution there. Now, what's interesting about that is that these two solutions are not necessarily just adding the period of 360 onto sine. What we have here is this would be 360 here. That's 360. And then this would actually be the quadrant 2 solution, which would be the 180 minus, you know, the reduction formula for quadrant 2. So this second one, like let's say that first solution was 30, or the given one, and then what that one would be a half on y. And then over here, well, that's going to be your quadrant 2 solution, which would be 150. So notice something about tan. No second quadrant solution. I had to go a full 180 degrees to find that second solution. So unequivocally and without any argument, we can say that we don't need two quadrant solutions for tan, everyone, just in case we're wondering, in case we've been told otherwise. So let's begin with the solution here. Now we've got reference angle is this. We should really ask ourselves, and I'm sure we all know that a positive value for cos is associated with quadrant 1. But the reason why I didn't go straight to that is because I really wanted to talk about this. See, we might say 1 and 3, but do we need the third quadrant? Nope. Right? And again, if that doesn't make a lot of sense, you really want to go back to your trig graphs from grade 10. Q1, right? That's what we're working with. Now, the formula there is just theta. So really all we're going to have, we're not going to have any reduction formulae involved. We're just going to have the acute angle. At this point, we're going to go to the reference angle and write it out as the solution. So we'll say, well, it's x, actually not theta, guys, about that. And so we'll just say x plus k 180 plus, oh no, well, there's no plus x, plus k 180, so 78. Yeah, x equals, excuse me. Okay, so the solution is x equals 78.69 plus k 180. Now, that is all well and good, but because we have to go a full 180 degrees and not a fraction, right? What we'll need to do is qualify that with k as an element of integer values only, right? No fractions of 180. Now, if anyone's wondering why we didn't have quadrant 2, it's because sine's got clearly two solutions close together there. That's your quadrant 1, that's your quadrant 2, that's plus 360. Tan, evenly spaced. No second, no other quadrant, no quadrant 3 for this. Okay, so that's this solution done. Now what we need to do is pursue this solution that we have on the left here. Well, that's fine. Step 1, follow standard algebra rules and just divide up by 4. So we'll have sine 3x equals -1/4. Following the QRS method, right, which stands for quadrants reference angle solution, we're going to say the quadrants are, or a negative sign, right? Which quadrants would it be? Like, I'm just going to get the cast diagram going over here. And what I would tell you guys, if you want to memorize your cast diagram, if you haven't already, write it on the top right of your page every time you do a question. Don't check your notes, right? Unless you forget. And that way it will live up here where it belongs. ASTC theta 180 minus theta 180 plus theta 360 minus. For anyone who's wondering, quadrant 1, 2, 3, and 4, right? If you write that out often enough, you'll be able to get it from memory. And it's not a bad idea when you sit down for your final to write that on your question paper somewhere so that you don't have to think about it after that. And you can refer back to it if you need to. So quadrants for negative sign, we can clearly see sign will be positive in those two. So it's got to be negative in those two. So we'll say 3 and 4, right? And now because this is not tan, and you can clearly see there's two quadrant solutions associated with sine, we are going to do both in this case. But let's see how that would go. First, we need our reference angle, right? Reference angle would be shift sine. And this is an important point. You ignore the negative because we've already handled the negative in a way. We've thought about where sine is negative. So anyone who's tempted to type that negative in, don't do that. You must leave it out. Just because you've dealt with the quadrants where it's negative, you treat your reference angle, you want an acute solution for that, or else it's wrong. So you want to say a quarter, basically, leave out the minus. And our reference angle is 14.48 degrees. Alrighty, so now we write the solution. We say x equals. Now, do we have a quadrant 1 solution? You see, we might be tempted to write 14.48, but we're not going to do that. We're going to say the sign is negative in quadrants 3 and 4, making it the case that I need to apply those reductions. So 180 plus 14.48 gives me 194.48 degrees. That is my quadrant 3 solution plus k, not 180 this time, 360, qualifying it as an integer only because again you have to go full period across to get to the next solution. And then, you know, we would say or, not and, right? Just like in grade 9 and 10. And then we'll say, okay, well, what's the reduction? It is 360 minus. So the 360 minus 14.48, taken from that. So, excuse me, 360 minus 14.48. We take that reference angle, and that gives me 345.52 degrees plus k 360. K is an element of integers, not forgetting that. Hey, they will not mark it right unless you have that. And now, just a word on how it's marked and how things go with this. You notice it's a level 4 question, it's 6 marked, but it's nice and routine. It follows sort of standard procedures here. We know the procedure, then we can get through it nice and easy. We don't have to think too much. And that's what makes the general solution a type of question that you really want to get. You know, work on them, make sure that you're getting those 6 marks because they're about the second most routine thing. The only more routine thing than that is your reduction formula question, which is also level 4, often up to 7 marks. Now, if we look at how marks are allocated here, they actually give you marks just for the solution that you have. So everything that all the steps that we followed before that are just for us, you know. And you can actually, if you're quick enough, you can just write the solution out. Like if we had a simple one, like if we said another one here, we had like sine x equals a half, I can go straight to x equals 30 plus k 360, or x equals 150 plus k 360, k e z, k e z. Now, did I not do the steps? I did, but I did them all mentally because mark allocation wise, like I'm not getting anything for all of this. So you guys, you know, do with that what you will. Like show steps if you need to, but if you want to go straight to that, if you're pretty sharp with these, you can.
Good to remember as well that that will be for the national exams. So when we talk about the mark allocation, you can only really apply that to the national exams because the trial exams, the marking is unfortunately all over the place.
It really comes down to what your teacher has to say.
And for school exams, it's even worse. You know, if your exams are internally set, then you'll see them allocating marks for all kinds of things. But you should really look at the way that marks are allocated in the final, because you can count on that always being the same.
Yeah, there's rules for these things. So if you take a good look at the memos from a trick, even any grade 11s you might be watching, learn those memos, get an idea of where the ticks are, because then you won't be wasting your time showing steps that you don't need to. Because where do we really need time? In paper 2, right? That's where we run out of time. So, all right. So that's pretty much the situation with this general solution. Let's consider the graphs. Down, and again, just taking this down. Remember that you can access this video again and take notes as you need to. But what we're going to try and do is get through as much as we can in the time that we've got, just to cover some ground. Okay. So the nice thing is that the general solution leads well into the graphs. We've talked about, the periodic nature of the graphs. We've talked about 180 for tan and 360 for sine. Let's see what we're dealing with here. So we've got a diagram which happens to be a cos graph, right? But it's been reflected in the x-axis and its amplitude has been changed to 2. We're looking at the interval -120 to 240. Okay, well, how nice of them, right? They've given us a sketching question for 6.1, which really isn't all that bad. Now, I know a lot of you guys go straight for this when you see sketching, but you really don't need to. You can sketch without the calculator. And I think what I'll do is first sketch it, and then I'll discuss how it would be done with the calculator. Many of you already know how to do it with the calculator. Let's talk about how we would do it without. So the first thing is we'd look at g of x, and we'd say, okay, that's a sine graph, but it's been shifted to the left. Plus indicates to the left, just like with algebraic functions, by 60 degrees. So what I'm going to do is I'm going to start with the axes, because that's what you guys would have. You would be given some axes, like a data sheet. Sorry, not a data sheet, but more like an annexure where you can sketch this graph on the same set of axes as that other function that you've got. So we're going to need to sketch both here. But anyway. All right, so 60 degrees to the left, right? So instead of sine starting at the origin, which this is what you can imagine, like starting at the origin like that, it's now going to start here. And I'm going to call that, I'm just going to write it there, -69. Sine would normally just go straight up there, and then go down, and we go up, like that, right? And so what we've done is we've taken the standard sine graph, which would have been at the origin, and we've shifted it to the left by 60 degrees. Now, what they want is us to indicate the intercepts of the axis. Now, because we've got the standard sine graph that's just been shifted a bit, the maximum is still going to be at 1, and the minimum is still going to be at -1 for those of you who know. If you don't know, let's take a moment to talk about the standard trig graphs. I'm going to draw all 3 of them. This takes us all the way back to grade 10, but it's good to know, right? So the sine graph, again, starts at 0, like so. That's right. There we go. That's an interval of the sine graph. Starts at 0, peaks at 90 and 1. Then we're basically adding 90 each time. So we've got the x-intercept at 180, trough at 270, or minimum at 270 if you want to use purely mathematical terms there. And then obviously it ends, or the next period starts at 360 degrees. And then you've got your minimum there in the negative at -90 and -1. And then you've got that x-intercept at -180. X, Y. So this is really your basis for understanding of the trig graphs. You want to know exactly where all of those key points are. And then when you see this one, you say, okay, well, what's happened to you? Because I know this one very well. You'll know this one very well. And you'll say, well, what changes have happened? And you'll see shifted 60 degrees. That's for other questions where you might need to identify, let's say, A or B or the K value or something like that. So you know your standard graph, and then you compare it to whatever graph you've been given. Okay, so
let's take a look at the standard cos. Now cos is interesting because it's symmetrical. So let's have a look. Start here, it'll do that. And you shouldn't really lift your pen when you draw it, but it doesn't matter too much. No one will notice. Okay? I don't notice it. And we've got an x, we've got a y. So it actually starts at its maximum, which is 1. These are very similar because you basically just take that sine graph and shift it 90 degrees. That's the curvature. And then another tan graph, different period. We looked at this one in the last example, that general solution, but there's the tan graph. Now, just a word about the tan graph, it doesn't have an amplitude. See, this one has a peak at 1, and it has a trough at -1, it has a maximum at 1, and minimum at -1. But this doesn't have maximum or minimum, this tan graph. But what it does have, that I know a lot of learners are familiar with, is a landmark point, 45 degrees. So I'm going to talk about this a little. Let's say I was showing on this very graph here that it was 45 degrees and 3. Some of you might already know that that means that the graph I just drew was 3 tan x. In the same way that if this was a 3 instead of a 1, this would be 3 cos x. Right? So be aware that at 45 degrees, that's basically what we use in place of an amplitude for that. Okay, so now that we've talked about the broader aspects of the graphs, I think it's enough. We're going to approach the question in earnest. I'm just changing them back to normal graphs because that's what we're using for reference. So it says, on the same system of axes, sketch the graph of sine x plus 60. So it's basically taking this graph, the sine x graph here, and we're shifting it to the left by 60 degrees. So instead of going through 0, it's going through -60. But now that peak you can see was at 90. We take 60 off of it. Maybe I'll just move that to the right a little. Yeah, that really wants to be over there, somewhere on the right. So excuse me there, guys. It really doesn't want to be at 0, that cos, because it hasn't been shifted by quite enough. It would be if you shifted it by 90, then it would be equal to cos. But it's been shifted enough to be that the peak is here on the right, and it's at 90 minus 60, basically. So we don't necessarily need to indicate that point, but just so you know, this was at 90 originally, now it's going to be at 30 degrees. But what they want is all the intercepts of the axes. So let's get started on that. We'll say that 0 degrees is now at -60. That 180, which would still be in the interval that they've asked for, yep, it goes up to 240. That 180 would now be shifted a little bit to the left 60 degrees. So 120, yeah, 18 minus 6 for that. So 120 is where the x-intercept is now. And then that 360 is going to be at 300. Now that's out of the interval that they asked for, because you see it ends at 240. So I'm not going to bother with that 300 degree. Now, let's see, -120 on the left. Yep, we're out of that range there as well. So we don't really need to show those bits of it. We just need those two intercepts, -60 and that 120. That's a 120. The endpoints. The endpoints. Yeah, they asked for the turning points and the endpoints. So actually, you know what? We do need this peak 90. So we're going to show the 30 and the 1, right? And then let's see, that one was at 270. That will be in the range now. We're in the domain. It will be 270 minus 60, 210, which is less than 240. So often we just have to show the intercepts of the axes, guys, and write the functions equation next to it, asking for endpoints, asking for turning points. That's a kind of trial exam type of thing. You won't tend to see that in the November exercise. So this one is 240, -1. It's a good idea to write it as a coordinate next to it. 120, 1, and then let's see, endpoints, right? So the endpoints are at the end of the domain. Yeah, it's going to be 240. 240. Now we might be thinking, how am I going to know what it should be at 240? Well, we sub it in. So
sine of, what was it again? It was, oh no, it was actually sine x plus 60. So we'll say sine of 240 plus 60, negative root 3 over 2. So we'll say 240, and which is actually over here. I'm just going to adjust it a bit. You guys are taking it down already, just adjust it yourself. Really want it to end right about here, which is, let's see, negative root 2. Yeah, negative root 3 over 2. 240 and negative root 3 over 2. And then the endpoint on that side, let's see, negative 120 degrees. We're going to go ahead and sub that in. So we'll say sine of negative 120 plus 60, negative root 3 over 2 on that side as well. So I'll just shorten it a bit, bring it up to about where negative root 3 over 2 is on y. And then I will say that that is negative 120, negative root 3 over 2. And you know what? That's more or less the graph that they've asked for here. So what is it at the end of the day? It's sine that's been shifted 60 degrees to the left. Okay, so so we got 4 marks for that. That's pretty good. And you can do that a lot quicker, you know, without the explanation, you can get those 4 marks in a few seconds, really. Now, let's see, 6.2, we've been asked to, so this is 6.1, yeah, and then 6.2, we've been asked to give the period of G. So 6.2.1, give the period of G. Now, it's a sine graph, so the period of it is 360. 6.2.2, range of f of x minus 3. So f of x is the function that was sketched initially. We're probably going to need to sketch it on these axes, because what you would have on your annexure that was attached to your exam is you would already have that graph on there. You would have drawn my graph here, so I'm going to probably draw that other one again in a moment. But yeah, f of x minus 3, if we take a look, we can see the current range is from negative 2 to positive 2. If we subtract 2 from that range, we're going to get this. Y as interval notation is, let's see, negative 2 minus 3 is negative 5, and 2 minus 3 is negative 1. So essentially what we've done there is we've taken the graph that we're given, and we've shifted it down by 3 units. That's a Q value. So Y shift, vertical shift.
They will be negative 4.
Negative 4.
Was the first one. First one's negative 4.
Yeah, that makes sense. And then the other one would be negative 2 minus 3. That's negative 5.
Sorry, no, you're right.
Really?
Yeah.
Well, it was 2. The maximum, just so you guys know, the maximum was 2. So we took 2 minus 3. That gave us these. 2 minus 3 gave us negative 1, actually. And then negative 2 minus 3 gave us negative 5. So yeah, this is what it is. It's y is an element of negative 1, negative 5. Okay, so the next thing, 6.2.3, they ask for the number of solutions to f of x equals g of x. So what's helpful there is to realize that it's a 1-mark question, first of all. Because you would have sketched your graph on the same set of axes as the original one, you will be able to see clearly how many solutions there are. Because what we should already know, and what is helpful to already know, is that f of x equals g of x, we're talking about intersections of the graph. So if I draw what they've got as negative 2 cos x, it's going to be like, let's extend it a bit to negative 2. And it's going to be going through, let's see. There's 19, negative 19. There's positive 90 there. And it's going to go all the way up to 2 here as well. And we get something like that. And we can see those solutions. So that's peak bottom 2, and that's a trough of -2. This function is f of x. This function is g of x. Look at those solutions here. There's one, there's one. So we write the answer 2. Now, don't be tempted to do a general solution for that. Not for 1 mark, guys. If it was 6 marks and they said give the exact, values, then we would just do another general solution like we did at the end of the question 5. Okay. Let's see. Now that's a bit of an interesting one. 6.3 asks for which values of k will g of x minus k equals 1 have no real roots. So what we'll need to do is take a good look at g. Now, what does g of x minus k equals 1 really mean? Well, we're taking g of x and we're subtracting a value from it. And then they're saying it should equal to 1. Now, if we're talking about roots, we really want it to equal to, we were talking about zero products earlier on, you want it to be equal to 0 on the right. So I'm going to bring that 1 over to the left to start. Because I'm saying now I'm taking g of x and I'm shifting it down by k minus 1. So the roots will be shifted down by that amount.
So we're looking for places where the graph is, we're looking for places where the graph is equal to 1 if we subtract k units from it.
Mm-hmm. Yeah, that's what this first part means. It means that if you take g of x shifted down by k units, which g of x is that one there, and then you move it down, where will it equal to 1? Now, what I can see is that it has a, did I get them backwards? Let's see. F of x is, yeah, I got them, no, I got them the right way. That's f of x. G of x actually has a maximum of 1, doesn't it? Because it's sine x plus 60. So this is interesting because what that means is that it would have to equal 0. That's what it means. Now, let's talk about why that is, because I just sort of realized that now. We're not going to need to do any of this. Normally you would. Normally you'd want to make it equal to 0 and see like exactly how many units you have to shift it down or up by. But in this case, where is it equal to 1? It's equal to 1 at the maximum. So if I shift it down at all, there's no values above 1. So
that means if k is less than 0, then there's no roots.
Yeah, that's what it means. Because
k is greater than 0.
Greater than 0, yeah, because there's a minus there already. But yeah, to just put it in simple terms, if we shift it down at all, that's not going to work. And so that means it won't have real roots. So at all means greater than anything, or any value, any actual value of a vertical shift downwards. So yeah, practically speaking, what we're saying is if we move it down at all, then it won't have a solution.
On the other hand, we can shift it up.
So let's see. The most we could shift it up by is 2 units.
Yes.
So what we would then do.
Now shifting it up, that would be a negative value of k. Right?
Yes, because now you do a minus minus, because if you have, for example, f of x is subtracted by -1 equals 0, for example. This is taking f of x and then shifting it up by 1 unit. So what we would have is we just put a upper limit on it of 2. -2.
Yeah.
And you don't want to move it up by more than 2 units, essentially. This is graphical interpretation, guys. You have to think your way through the question practically.
You had something the right way around first. Yeah, so we can't shift it down at all, but we can shift it up by less than 2 units.
Less than 2 units.
So k should be positively greater than 0, but less than
2.
-2.
Yeah. Well, if it's less than -2, you get up by more than 2 units, and that would give you no real roots. Yeah, that's right. Yeah, you see, they've actually asked for it won't work. They've asked for no real roots. So what that means is, okay, so this should actually be the 0 should be, well, the 0 can be there, but these should be, let's see, greater. And you shouldn't really have them facing to the right, eh? So what would be the best? It would be putting the -2 on that side, 0 on that side. And that was saying greater than -2. greater than 0 would give us non-real roots. Yeah, but this is it. Less than and equal to -2.
Yeah, no real roots. So it's going to be two separate
I'm
regions.
thinking, isn't it? Or
Yeah,
it's all
two
yeah,
separate
That's what it
regions.
is. Excuse me, Gary. It's all. Yeah.
Yeah. So what Murray's saying there is that you can either shift it down and then the graph won't have a height, it won't intersect a height of 1, or you can shift it upwards by more than 2 units, and then at that point you won't have real roots. You'd end up moving the minimum up past y equals 1, and at that point the graph won't intersect at that height. So if you guys are battling with these types of questions as well, it's a very good idea to go through grade 11 functions and to go through the types of comparative graph questions where, we asked to find where's f of x greater than 0, where's g of x greater than 0, because those same skills are tested in trig functions, but they're not really retaught. So you should go through the normal grade 11 functions for that. And also you want to look at the types of graph questions where there's translations and reflections and stuff like that. This is all part of that section. This is a very tough example of one of those questions. So
there's a bit of thinking to it. When it comes to graphical interpretation, it really just depends on how you're doing on the day, I would say. You can do it quickly. It might take you a bit longer. The questions are all about the same in a way. So yeah, the idea is that you want to move it upwards by an amount that is no more than 2. So because it's already negative, which they like to do in the trick, they make it negative. So you have to think about that. And you have to say, I'm going to be minusing a negative, but so it shouldn't be less than -2. And then we're saying, I don't want to move it up by any amount. So we'll move it down, sorry, by any amount because of the negative. So I'm saying greater than 0 will give me a solution that isn't real. Okay. So graphical interpretation, it's really the last thing that falls into place for functions. So anyone who's finding it a bit intimidating, learn everything else first. 6.4, the graph of h is obtained by reflecting g in the line x equals -30. Write down the equation of h in its simplest form. Okay, that's quite an unusual one. It's mostly because it's a trial exam. Things like that don't tend to show up in the final. But the idea of it is that we're reflecting g in the line x equals -30. So that's a vertical line, in case anyone's wondering. X equals references a vertical line through -30 degrees, which would be here. 60 is over here, -60, so -30. There it is. There's that vertical line, x equals -30. And then basically what we're going to do is we're going to say, okay, g, which was, let's see what g was. G was sine x plus 60. So if we reflect that graph there, we have to think to ourselves, okay, we've got -30 there, we've got -60 there. So if I want to move that across, I'm going to say there's a difference of 30, so it's going to go through 0 now. And it's going to have symmetry through there. So it's basically going to look like that. Instead of going up over there, it's going to go up over there. And its peak, which was at 120, which, what would that be from -30? Let's see, 150 degrees, right? Well, I'm going to take -30 and I'm going to subtract 150 from it. And that gives me a peak at -180. There, we would have a peak at -180. Which is again the same distance on either side, but a distance of 150 there, but it was 50 to that peak. Okay. And the line of symmetry, you can see them crossing it. It's x equals 30. And so let's finish off some of that. And so now we see what it looks like more or less. And so the equation of h essentially would be a negative sine graph, because now it goes down from there. And we're not reflecting it in the x-axis more or less, but sorry, in the y-axis more or less, but it's something like that. We're reflecting it in another vertical line. So let's write the equation down. 6.4. What we have is a negative sine graph. And how far has it been shifted? Now, there's a number of ways you can write an equation like this. You could write it in terms of cos if you want it, because of the curve ratio. But we're going to write it in the most similar way we could, more or less. And so it's going to be a negative sine graph. But if we look at it, has been shifted. Let's see. It's negative 180 is where the peak is. The peak is normally at negative 90. So it'll be shifted to the left by 90 degrees. Negative sine x minus 90. But that's actually plus because we went to the left. And then if you look at that now, x plus 90, let's see, that's a cos graph, isn't it? So what I get with that, negative cos. That's what we would get if we reflected it through that vertical line. All right. So that is 6.4. Now, the next thing we'll be working on is 3D trig. You can, if you like. Quite the easy one for 3D trig there. It's got all the values given. But then it looks like for 7.2 we've got non-numerical, which is the good stuff.
Great stuff. Thanks very much, Mark. No problem. So quite a tough graphs question there. No general solution, unfortunately. So just a reminder, guys, we are working on the 2025 trial, paper 2. That's the KZN trial, paper 2. And it is, it's this year's trial, KZN paper 2. We just finished off the trig graphs. So in trig, we've got the basics, we've got the graphs, and then we've got the 3D trig. So the 3D trig, the 3D and 2D trig. Okay, so we've got question 7. Let's have a quick look at that. Okay, so it says, in the diagram, CD is a vertical pillar, and A, B, and C are points in the same horizontal plane. AD and DB are straight cables. CD is 15 meters, BD is 20 meters, ADC is 28 degrees, and ADB is 52 degrees. So this is a 3D construction. And so we need to basically see here that ADC is the floor. And then we've got a pair of like vertical walls, ACD and BCD. And then there's a sort of slanted plane, ADB. So yeah, it's important to remember going in right away that that wherever you've got a right angle triangle, you should probably be using definitions. So in this section, the 3D and 2D trig, we're using those definitions, Sokotoa, right? Because these so you have the opposite, adjacent, and the hypotenuse, and then we're using the rules for 2D trig as well. So A over sine A is equal to B over sine B, C over sine C, and A squared is equal to B squared plus C squared minus 2BC cos of A. So those are the rules that we're going to be using in this section. And then the area rule as well. The area rule comes up every once in a while, but it's not as common. Okay, so here we've got a numerical example, which is actually really easy and not super common for trig. Normally we are only given variables in grade 12. The first thing they want us to do is calculate the length of AB. So if we look at where AB is, what we're going to do is going to back to the board. Okay. If we look at where AB is,
it's in two triangles, it's sort of the floor and that slanted plane. So we're probably going to need to work with the triangle in the slanted plane. And if we look at that triangle, what we've got there is we've got 52 degrees, we've got 20 meters. Yeah. Now, that's not enough information to work out AB. So we need to look at the other information that we've got. And what we've got is we've got a triangle that's coming down there on the side of the pyramid, which has a height of 15 and an angle of 28 degrees. So we're going to use this information in the smaller triangle, and we need to bring that into this triangle. So what we're going to do is we're going to work out the length side between them, which is side AD. Now, AD, if we're looking with relation to that angle at the top, this is what AD looks like. It is a 28 degree. At the top, it is C, A, and D. So we know that that's 15 meters. If we want to work out AD, what we will say there is that AD is equal to, or rather start with the angle, right? We want to look for the adjacent over the hypotenuse. So we can say cos of 28 is 15 over AD. And then we isolate AD. So we will multiply the AD up and divide out the cos 28. We have AD is equal to 15 over cos 28. Okay, that will give you a numerical value. And you can work that out, but don't round off just yet. What I would do is probably leave it as 15 over cos 28. But it's equal to 16.9885 or 9886. We don't want to round off to too few decimal places. We don't want to round off to too few decimal places because it's not the end of the question. So we're looking for this, and AB is if we look at what we've been given there, we've got this side. Look at triangle ADB. We've got the 20, we've got an angle 52 degrees, and then we've got this side now, which we found to be 16.9886. So we've got two sides and an angle between them. And whenever you've got two sides and an angle between them, you want to use the cos rule. So we're going to use the cos rule for that. And let's just label it x. So x squared is going to be equal to that squared plus that squared. And if it helps, you can just write down the cos rule first as well. So a squared equals b squared plus c squared minus 2bc cos of a. Now, if you're looking for x, then that angle, if you're looking for this side, then the angle across from that side would be the angle that we fill in there. So it will be x squared equals 16.9886 squared plus 20 squared minus 2 times 16.9886 times 20 cos of 52. Okay, so look at that. We've got our two sides, and then the angle, and we just want to enter that into the calculator. So and that is going to give us 270, right? So we need to square root it. And we get 16.44.
And we want to just check the units as well. Now everything's in meters here. So yeah, that's a common mistake that I'll see as well. Sometimes if one side is given in meters, another side is given in centimeters, you've got to convert to 1 unit. And then your answer must have some kind of unit in it, right? So yeah, in this case, everything was in meters. We must mention that it's in meters. Okay, so 2. And 2, it's a completely different type of question. So these are the tougher ones, right? We've got variables involved. So there we see that J is a point on side HL of triangle GHL, such that HJ is equal to JL, which is equal to K units. And we can see that they're both labeled there as K units. Angle H is A and angle HGJ is B. So everything is labeled on the diagram there. You just want to double check that everything's labeled. If there are things that are not labeled, then you want to make a special mental note of them and or fill them in on the diagram. So yeah, in this case now, this is the classic sort of 2D trig problem where we've got a pair of triangles. Most of the time, you're only going to have information in 2 of the triangles. In this case, they only are 2 triangles. We have to bring the information from the one triangle into the other triangle using the link side. So let's look at how to do that. Let's look at how we do that. So I'll redraw this one because it's quite yeah, I'll redraw this one because it's quite a simple diagram. So it is H, G, J, and L. Okay, so that's all about information. And they say prove that the area of angle GJL is K squared sine A over sine of A plus B over 2 sine B. Now we're looking at GJL, which is the right-hand triangle here. And we've only got like one piece of information there. So what we want to do is try and bring all the information out of this. We want to try and bring all the information out of this side of the triangle and into this one. And the way we do that is using this link side, GJ. So we want to express GJ in terms of all this information, or as much as possible. And in order to do that, I think we just want to use the sine rule because we want to use the sine rule rather than the cos rule whenever we can, right? So over here, GJ over sine A is equal to HJ over sine B. So we pair them up we pair each side up with the sine of the angle that's across from it. And then we get this. And now HJ was actually, it was K, right? It's K units long. So now we can write down that GJ is equal to K sine A over sine B. But we're not quite done, right? But now what we've got is we've got that link side in terms of the other 2. So why do we want that link side? Well, when we're working out the area rule, when we're working out the area using the area rule, we need to have, just like with the cos rule, we need to have a pair of sides and the angle between them. So we already got this side K. What we want to do is get this side GJ. And then we're also going to look for the angle between them, which is J2. So J2, using the exterior angle rule of the triangle, we can say that J2 is equal to 180. Oh, sorry, it's just equal to A plus B because it's the exterior angle. It's equal to the opposite 2 interior angles. Now, generally, you don't have to give rules in the 2D trig, Euclidean rules, but you should write them down just to be on the safe side and to stay sharp. So it is exterior angle of triangle. Okay. And then what we're going to do is we're going to apply the area rule, because we've got GJ, we've got JL, and we've got J2. So we've got two sides and the angle between them. So the area rule is area of triangle GJL is equal to a half times A times B sine of C. So that will be A, that will be B in any order, and then that will be the angle between them, C. So it's going to be a half times K times GL, which we know is K sine A over B over sine B, sorry. Sine of angle C, and that was the angle between them, which we said was A plus B. So you can already see we're kind of getting close to, well, we've actually got what they want. We just need to bring everything together and rewrite it. So we look at what needs to be on the top there. We've got a 1. Anything that doesn't have a denominator is on the top, right? Because it's over 1. So that's K over 1. That's sine of A plus B over 1. So we will multiply everything that's on top together. It's 1 times K. The 1's not going to make a difference. So K times K, which is K squared, sine A plus B. And then on the bottom, we've got 2 times 1. The 1's don't make a difference, so it's just 2 sine B. And we double check if that is correct, and yes, that's exactly what they've got. So just by following that format, right, I could predict which way they were going to, require us to answer the question, right? We've been asked something about this triangle, so we actually start in the other triangle and use that triangle to express the link side in terms of all the variables that we've got in that other triangle that we're not being asked about. Once you've got the link side, then you can go applying the rule to the triangle that you've been asked something about. Okay. Okay, so that is the 2D trig done, and we now find ourselves coming to the Euclidean. Okay, so we're going to start with trig and Euclidean today. Doesn't look like we'll have time to get around to the stats and the analytical, but yeah, we will have more sessions for the maths, and we'll have more sessions for the physics as well over time. So just subscribe and stay tuned for that. Okay, we're also now, so just a reminder that this is the September 2025 KZN trial, right? The 2025 KZN trial. And we're moving on to question 8. Let's have a look at that. So, no. So question 8.1, we've got a circle there. In the figure below, O is the center of the circle. P, Q, R, and S are points on the circumference of the circle. And QR is equal to RS. So O2 is equal to 2x. Okay, so everything's labeled there. A good thing to remember when you look at Euclidean questions like this is sometimes they will give you tangents, and you have to remember that it's a tangent. In this case, we don't have a tangent. On the other hand, you want to be on the lookout for cyclic quads and tangents, because it's not easy to see them on the diagram. Like sometimes it's a good idea to highlight the tangents and the cyclic quads when you're going into it. But yeah, that's just a helpful tip. Then looking at this, we're just going to apply some basic rules. So it's one we can get through quite quickly. That's another good piece of advice. When it comes to exams, you should try and work quickly and carefully, but mostly quickly through the easy stuff. The stuff that you know is easy, you can work through it quickly, and then you know that those marks are in the bag. Don't go tackling the difficult questions that you have to sit and mull over
until you've worked through all the quick and easy marks in the exam. Then you'll find that, even if it's half the paper that you have to sit and think about, you have gotten all the marks for the quick and routine stuff already. So then you can go back. You're allowed to attempt the paper in any order as long as you label each question carefully. And you should try and keep question 5 together, try and keep question 6 together. So you don't want to do some of question 5 in different places, but you're allowed to attempt the paper in any order. It says that in the rules of the exam. So you can start with question, obviously in the stats, you would want in paper 2, you would want to start with the stats and the analytical. But then if you're finding the trig tough, go do the easy Euclidean, get it out of the way, and then come back. You are allowed to do that. Okay, so 8.1.1, they're asking for QRS. Now, in that diagram QRS, we see that we're going to need to use angles at the center there. So, okay, I'm just going to check the screen again because it'll be easier to work through this diagram. Okay, so we're looking at QRS then. What we see is that that angle at the center, O2 and O1. Now, when it comes to angles at the center, there's a couple of different constructions for angles at the center, and this is the least common one. It's the one that you see least often in the exam.
The 3 different types of constructions you'll see for angles at the center. The normal one, most guys can manage with this. If this is your chord AB, and there's the center O, then you have another point C, right? This angle over here is going to be 2 times that angle. So it kind of looks like a cursor or like an arrow symbol. That's probably the easiest one to recognize. Then you've got another one which looks kind of like angles in the same segment. But you don't want to get confused between this one and angles in the same segment. So there we've got a chord which is subtending an angle C at the circumference, but it also is subtending at the center. And this angle will be 2x, and this angle will be x. So there it kind of looks like that bow tie shape that they talk about, but really what's happening is a chord AB is subtending an angle at C, and it's subtending an angle at the center. And if it subtends an angle at the center, it's always going to be double the angle at the circumference. So this, if we had to subtend another angle from AB, we'll call that D, then that would also be x. That's angles in the same segment, right? Angles in the same segment will always have both of the angles that are being subtended on the circumference. Whereas, if one of them's at the center, it's angles at the center. But this one, this is going to be the most tricky thing. This is going to be the most tricky thing for most guys when they look at this question. This is the 3rd type. So what happens here is we've got our chord AB, and we've got the center there at O. And then the angle that's being subtended is actually back in the minor segment, right? Going back from an AB into the minor segment. And that is our angle C now. So when that happens, this angle C is not actually related to that angle. It's related to the reflex angle on the outside there. So if this angle C is x, then the reflex angle will be 2x. And that's important for us because they've actually given us this angle at the center here. They've given us the acute angle, or the obtuse angle, the non-reflex angle. They've given us that as 2x. So we're going to have to start by working that out. Okay. So you guys are really going to want to open up the paper for the Euclidean section because there's a lot of stuff that you would want to look at the diagram for. So angle O1, right, is 360 minus 2x. Angle O1 is 360 minus 2x, and that's because of angles around a point. Right, or you can just say revolution. I like that one. Right, so it's 360 minus 2x. And then, okay, let me just draw this diagram very quickly. Okay, so we said that O1 is 360 minus 2x because it's a revolution. And then from there, we can say that this reflex angle is equal to double the angle R. So that's what they're asking us for. QRS is that whole angle R, right? So you really don't want to be in grade 11 and grade 12 and still battling with the 3-point naming scheme. Remember, if you are battling with the 3-point naming scheme, then what you should do is read through the 3 points Q, R, S. The angle is going to be the one at the center, right? And it's going to be between the two lines that are drawn, so between QR and RS. But yeah, if you're battling with that at this stage, you really need to get that under control. It will help you a lot. So QRS now is going to be a half of 360 minus 2x. And the reason there is going to be angles at the center are 2 times angles at the circumference. Okay, and half of that is going to be 180 minus x. So we distribute that half. Okay. And there we're done. 2 lines, 2 reasons. Okay, next they're asking for Q1. So that's that angle over there. Now, the first thing we should notice about that is we've got an isosceles triangle there. So because QR and RS are equal, that means Q1 and S2 will be equal. And if we know any one of the angles in an isosceles triangle, we can work out the other ones. That's always going to be the case. So for 8.1.2, right, 8.1.2, we are looking at Q1. Now, what we do there with an isosceles triangle like this is we know what R is. So we can say that Q1 is going to be like 180 minus R over 2. But we've got to be careful with this because they want us to start, it's for 3 marks, first of all. So that should remind you that they want us to start with stating that the angles are equal. So we should say Q1 is equal to S2. And that would be equal angles, opposite equal sides. You've got to be very careful with that. And now that we've stated that they're equal, we can say, therefore, R, or QRS, that's what we called it before, QRS plus 2 times Q1 is equal to 180. And then sum of angles in the triangle. Okay, so the reason why we say 2 times Q1 is because the 2 base angles are equal. So these are both equal to Q1, right? And now QRS is 180 minus x. And when we bring that across, the 180s will cancel. So 180 minus 180, that cancels. And the negative x becomes a positive x. Okay, so 2 times Q1 is equal to x, and then we get Q1 is a half x. Okay. All right. So that's the size of Q1, and it will also be the size of S2. Then lastly, we've got angle P. Angle P is across there, and that's really easy, right? S2 is equal to Q1. We've already stated that, and they know that we have because it's only worth 2 marks. So angle P is going to be equal to angle S2. And that is going to be a half x. Right? Both of these angles were a half x. And the reason they're angles in the same segment. Okay. Now, one thing you'll notice here is that we only have reasons really when we start setting up an equation. Once we've set everything up and we're just isolating things and simplifying algebraically, all those algebra steps don't really require an equation. Okay, or they don't require a reason. Okay, and then the next one, 8.2, is a Euclidean, well, a grade 12 Euclidean question. So let's have a look at that. Okay, in the diagram, triangle, okay, sorry, let me share my screen. In the diagram, triangle ACE has point D on CE and F on H, and F and H on AC, such that DF is parallel to EA. DF is produced to G. AGB, GH, and BC are drawn, with BC parallel to GH. If HF is equal to FA, and DE to CE is 2:5. With BC is parallel to GH, HF is equal to HA, FA, DE to CE is 2:5, and then BG is 12 units. So we're definitely going to be using proportional intercept theorem here. And a good thing to remember in these types of questions is we're either going to be proving that triangles are similar, or we're going to be using the proportional intercept theorem. That's like 90% of what we do. So the grade 12 Euclidean gets a bad rap. Everybody's scared of it, but it's mostly because I don't know, the people are not really teaching the fundamentals and sticking to the fundamentals. So we've been asked to calculate the length of AG here, and we can see first of all that AG is a part of the triangle AGH, and then there's another triangle ABC which has a parallel base. So a lot of what we're going to be doing here is just bringing the ratios of the sides across the triangle. Okay. Now I'm going to read all this quickly, and then we can work on that. Right, UG, CH, those two are parallel. We've got A, E, and GB. Okay. There's a straight line. Yeah. Okay. Let's label everything. CH, FA, and BGA. Sorry about the alarm there. So next door. Okay. So those are all our sides labeled. And then what we're going to do now is we're going to calculate the length of AG. So we want to look at what ratios we were given. We were given DE to C. Okay, so there's DE and there's CE. All right. It's important to note which sides are parallel. So these two sides are parallel, and then you've got these two sides, which are parallel. That means we can take this ratio across this triangle, across the parallel lines. So CD and DE, they're in the ratio 2:5. So we can just fill that in. And then on this side over here, we see that corresponds to FA and CA. So FA to CA is also 2:5, and we should write that down as part of our reasoning. So we're going to, as part of our working. So we'll say that And I like to work with fractions rather than ratios. So you can do it either way. You can say DE over CE is equal to AF over AC, which is equal to 2 over 5. And the reason there is Proth theorem. So whenever you use the parallel lines, the reason is going to be Proth theorem. If you use a similarity statement, then it will be similar triangles. Okay. Now, we can't take this ratio directly across to get BG and GA because BG corresponds with CH and GA corresponds with AH, right? So those are the two sides that we want to work with together. So we're going to need to work out some of this stuff in terms of X. And so we can just label this side AF as 2X, right? Then we know that AC would be 5X. And that will allow us to work out the rest of the parts of the line because HF is equal to AF, so it's also 2X. And then if the whole thing is 5X, that means that CH is going to be X units long. The way that we would do that is we just say 5X minus 2X minus 2X and 5X minus 4X, right? That gives us X. So now we know all the parts in terms of X, and that's going to enable us to take this ratio across the triangle. So luckily there's no real working for this. We can just say that BG, there's no reason for that, that is working. We'll say that BG over GA or BG over AG, right? This side and that side is going to be equal to CH over HA. Which is equal to X over 4X. And that's just 1 over 4. Okay. So the reason here is going to be Proth theorem because as we make that ratio, we're also bringing it across the triangle to BG and GA. So that's going to be Proth theorem. But there's no reason for how you got the X over 4X. You don't have to worry about that. You can split these up. So you don't need to try and say like HF is equal to AF, therefore it's equal to 2X, and CH is equal to 5X minus. You don't have to worry about all of that working. You just need to set this up like that. And so it's in the ratio of 1:4. Now we've got the ratio of BG to AG. And we know the length of BG. So we can say that, let's just write down BG over AG equals 1/4. And then we'll fill in BG as 12 units, which was given in the question. 12 over AG is equal to 1/4. And then cross multiplying there, we have AG equals 48. And it is 48 units. So you should check if it's centimeters or meters or units. It's 48 units. Okay. So we're kind of winding down now, guys. Obviously, we're not moving super quickly through stuff because that would defeat the point, right? We want to make sure that we go at a pace where we talk about all of the different concepts that are involved. And there's a lot more to say about each one of these questions, that each one of them. What we're doing here is summarizing weeks and weeks and weeks of work. So we're trying to give you pointers of where to go back and look and where to study to improve your foundations while we go through these different types of common exam questions as well. So there's a lot to look at. Now, what I'll do here is I'll go through question 9 and then we'll move on to the Q&A. So I just need to redraw one diagram here. You guys will bear with me. So hopefully by next week, I'll get my streaming program set up so then I can just work on the diagram on the screen for these questions. But for now, I'm just going to redraw the diagrams. So after this, I'll be taking some requests, questions that you guys have been battling with, and Murray and I will work through them with you. Okay. So first of all, let's look at question 9 here.
in the diagram, the circle with center O passes through F, S, H, and G. D, F, and DS are tangents. Okay, so we want to mark those tangents like this. Okay, we might just work on the page like this one. There's DF. It's a tangent. So we know that there we've got a tangent and a chord. And then DS is also a tangent. So there are tangents to a common point, right? But you want to mark off the tangents. Because of that, we know they'll be equal in length. But you also don't want to be too keen in the beginning. You don't want to mark off too much information on the diagram because it can become messy, and at that point it's counterproductive. SG is parallel to DF, okay, and that is shown there. SG, DF, and then the diameter FOH intersects SG and R. Now, the first thing you should think of when you see diameter is it's going to subtend 90 degrees, right? Angles in a semicircle. So where is the diameter? There's the diameter FH, but unfortunately, FH is not subtending any angle. So if you think S2 is going to be 90, you need to be very careful. You need to rethink some of this stuff because it would only be 90. Like FSH would be 90, but FSR, that's not 90. Okay, so just be careful with those. You want to pay special attention to angles that are subtended by a pair of points, and you've got to basically it's going to be a triangle where all 3 points are on the circumference and R is not on the circumference. So you've got a problem. Now they want us to prove that DSF is similar to OGH. Remember, when you're proving similarity, you just need to show that that 3 pairs of angles are equal, right? You can also do that by showing that the sides are in proportion, but you'll know those questions very quickly. You'll be able to identify them very quickly because you'll be given a lot of ratios or a lot of side lengths. And over here, we haven't been given any side lengths. So we're probably not going to use sides in proportion. We're going to use angles. And the triangles that we're looking at are DSF. That's the one with the tangents to a common point. So we'll make a note right in the beginning that these two sides are equal. And then OGAH is down there. OGH has OG and OH, which are both radii. So there's another pair of equal sides. And so it's probably going to be very helpful for us to note that, because if the sides are equal, then the angles will also be equal, right? And that means that angle G is equal to angle H, angle F1 is equal to angle S1. And so if we can find either F1 is equal to H, or if we can find G is equal to S1, then we'll have basically proven the whole thing, as you're going to see now. So first thing here is, the first thing that I'm spotting is that H is actually equal to S2, because they are angles in the same segment. They're both subtended by FG, even though FG is not drawn there. And then the other thing is we've got these parallel lines. So F1 is equal to S2. And if that's the case, then F1 is equal to S2, which is equal to H. We've just shown that a pair of those base angles are equal. And so let's look at how the working is to go there. Yeah. So we said that, forgetting, F1 is equal to S2, and that's alternate angles. Right, we've got the Z shape there. And when you list alternate angles, you should also mention which lines are parallel. So it's DF parallel to SG. Okay. Then we're going to say that S2 is equal to H, and that's angles in the same segment. Now, that means that F1 is equal to H. You don't need to write that out explicitly. Okay, and then we're going to state that we're going to move on there. So we can say
F1 is equal to S1 because we've got tangents to a common point. Now, this, you want to be careful not to skip over things. If you're in the final exam, you want to write there that df is equal to ds first. df equals ds, tangents to a common point. So because they're tangents to a common point, they'll be equal in length. And then we're going to say F1 is equal to S1, equal angles opposite equal sides. And then we're going to do the same thing in the other triangle, but with equal radii, you can skip that. You can just say that H is equal to G. H is equal to O G H, right? That's G1 and G2 because of equal radii. Now at this point, we've pretty much got everything we need to start with the similarity. So we've shown that a whole bunch of angles are equal here. If you can picture that, just remember we're showing that like 2 pairs of angles, so 4 angles are all equal. Now we can say that F1 is equal to H. S1 is equal to G. We'll say proven for both of those because we've given reasons. And then lastly, D is going to be equal to O1. And that will be sum of angles in a triangle. Okay. So that's a lot of working. Sometimes you get 6 marks just for the similarity proof. So this is a long question for 6 marks. You've got to be very careful with these usual types of questions, showing that a pair of, isosceles triangles are equal. It's not something that I've seen in another paper. So that's a new one. And then we can say therefore triangle DSF, I think that was the angle, the ordered triangle DSF is similar to triangle OGH. Okay, and the reason angle. I see a lot of guys forgetting that. You've got to give the reason for your statement at the end. Yeah, and then I think I'm going to leave it there and move on to the Q&A. Just some notes on these similarity questions as well. So yeah, please do send through your questions if you do have questions you want me to go through with you guys. Just some notes on this. You want to make sure that you keep all the angles from the one triangle on the same side. So notice I've got D, S, and F all on the left-hand side, and then I've got O, G, and H all on the right-hand side. You don't want to chop and change and mix them up. And then for most triangles, the order is going to be very, very important. In this triangle, we had a pair of angles that were equal. It's an isosceles triangle, so the order is not as important. But I still tried to stick with the order that they gave us: F and H, S and G, D and O, right? So I didn't swap these ones around, even though all 4 of them are equal. You want to, when you're naming the triangles that are similar, you want to stick with the orders, with the order that they appear. So DSF and OGH, especially if it hasn't been given to you, if you haven't been asked to prove that a certain pair of triangles are equal. Like let's say that in the middle of a question, we decide that we have to prove that a pair of triangles are similar in order to get some similarity statements, to get some ratios. Then you want to make sure that you name the triangles that you've declared to be similar in the same order that you found the angles here. But yeah, that's pretty much it. The Euclidean here is not that difficult, but obviously the rules are not that difficult there. But obviously this is a weird type of question, proving that 2 isosceles triangles are similar to each other is a bit of an unusual one. Okay, I'm going to check and see if there are any questions that have come through there. You guys can also just tell me, the year and the question that you want me to go through if you've been working on one and you've gotten stuck. And then I will take a look at that. I'm just going to check the WhatsApp quickly as well.
Okay, how do you prove riders? So there's a little bit of there's something to unpack there in that question. The first thing is, what is a rider? What is a rider? So the first thing, so we need to know first what a rider is. And a rider is basically just a fancy name for a geometry problem, right? So geometry problems where we are asked to, show that angle S1 is equal to angle S2, that's a rider. It's a rider because a rider is basically in math, it's like a proof light, right? So a proof, a proper mathematical proof is going to have lots of supporting theorems. It's going to have lots of evidence. Normally, it's like a full paper, and it shows that a pair of things are equal. Whereas a rider just uses supporting proofs to prove that one thing is equal to another thing. So a rider is case specific, whereas a proof is more general. So the proof questions are typically going to be the ones that you learn, right? If you remember in paper 2, we've got the grade 11 proofs, and you should look these up and know them, right? Learn them. There's the proof of tan chord, that's the most common one, proving that the angle subtended between a tangent and a chord is equal to the angle that the chord subtends. Then there's the opposite angles of cyclic quad, proving that they're supplementary, right? And there's a number of constructions that you have to do for that. So for tan chord, for example, this one is so common, we've been through it a bunch of times, right? You'll have a construction that looks like this, and you get asked to prove that this angle is equal to that angle. And what we do is we set up the equal radii there. We let this one equal to x. We've got radius is perpendicular to tangent, so this one's 90 minus x. This one's also 90 minus x. Over here we get 2x using some of the angles in a triangle, and then that one's equal to f. So that proof is proving that the angle between a tangent and a chord is always equal to the angle subtended by the chord. That's a proper mathematical proof. Now, if they had just said, prove that angle P1 is equal to angle T, then that's a rider, So the riders are just normal. The 90% of the geometry questions that you go through are riders. That question where we were just asked to show that a pair of triangles are similar, that's a rider. So generally, we don't prove riders. What we do is we solve riders, and we prove theorems. So those are two different things, right? So these proofs that we're learning, they're all proofs of theorems that we've learned. And the riders, the problems that we work through, those are geometrical riders, where we use reasons to support a statement. I hope that helps. Also I find a lot of guys are confused about, the proving questions. So the proving questions that are riders, they're not proofs. Like all the questions that we've done so far where it says show that or prove that this angle is equal to that angle, or show that these two triangles are similar, or show that these two sides are in this proportion, those are all riders. And we solve them. We generally don't prove them. Okay, some of the other grade 11 proofs that you will need to know as well is we've got tan chord, opposite angles of a cyclic quad. Then there's the line from center bisects chord.
Okay, that's a good one to know as well. And then I've seen in some rare papers, I've seen angles in the same segment. So if you can find that one, that's a good one to learn, but only once you've learned all the other ones. And then we've got the grade 12 proofs. Oh, sorry, and the grade 11 stuff as well. Proving the sine rule, cosine rule. The cosine rule is kind of tough, right? And the area rule. And then lastly, we've got the grade 12 proofs, which are just, there's only 2 of them. Similar triangles. And proving that similar triangles are in proportion, and then proportional intercept theorem. So those are the proofs that you need to know, that you need to study and memorize. Yes, so there are a number of rules when it comes to showing that a certain construction is a special type of quadrilateral. So obviously showing that something's a cyclic quad, we can do that in 3 ways. Right? There's 3 different ways to show that something's a cyclic quad. We can use the opposite interior angles. If we can show that any of those opposite 2 interior angles are supplementary, then that shows that it's a cyclic quad. It's the interior angles are supplementary. The exterior angles, yes, very good. The exterior angles, of course, you know that. The exterior angles are, if you can show that the exterior angle is equal to the opposite interior angle, that proves that it's a cyclic quad.
And the concyclic points.
Yes, the concyclic points. So this is the one that it's actually the most common one, but it's the most overlooked one as well. If we can show that we've got angles in the same stepping, then that automatically shows that it's a cyclic quad. So over here, if we can show that that angle is equal to that angle, or if we can show that that angle is equal to that angle, then it's a cyclic quad. And that's because
one's a chord and the other 2 are points on the circumference.
Absolutely. So this is a chord, right? If AB is a chord and then it's subtending to, and then it's got 2 equal angles, then those 2 angles would have to be on a circumference, right? Because we know that equal angles, that chord will subtend equal angles on the circumference. So if it's got equal angles, then they must be on a circumference, and therefore it's a cyclic quad.
It's a good idea to mention that in the cases where we have to prove it, normally the circle, yeah, you're taking that.
Yeah.
Normally it's not there. So you're looking at a quad of some kind. You're saying, does it have that feature?
Yes.
And therefore then you could draw a circle around it theoretically.
Yeah, that's very true. So that's a type of, this typically would be a rider, because they would say show that ABCD is a cyclic quad, right? But it's not a special type of rider. It's just a rider that's based on a converse theorem, right? So that's number 1. And then these are the converse cyclic quad theorems. That's what they are. So rather than saying because it's a cyclic quad, the angles will be X, we're saying because the angles are such, it will be a cyclic quad. And that's just the reverse of the theorem, which is called the converse. Okay. Then lastly, I'm not sure if we're probably asking about these, but there also are the situations where they say prove that ABCD is a parallelogram, prove that it's a square, prove that it's a rhombus, and that's actually quite a big complicated question, because there's a number of different proofs for each one of the different quadrilaterals, and this is one of the reasons that grade 10 maths is actually quite problematic, especially if people are not really good at those quadrilaterals. Yeah. Those grade 10 geometry, a lot of guys battle with these. They sort of also don't want to accept the reality that you have to learn all of those quadrilateral proofs. Some of them have never even seen the quadrilateral proofs before.
You can actually memorize every single quad property.
Yes.
Awesome.
Yeah. But the thing is, even if you know the quad properties, you have to know which ones can be used in combination to prove that something is a quad. And that is really the tricky part of this. So, for example, with a parallelogram, there's the 2 main ones, which are if you prove that it's got a pair of parallel opposite sides, right? If you prove that both pairs of sides are parallel, obviously it's a cyclic quad. If you prove that one pair of sides is parallel and equal in length, that proves that it's a cyclic quad automatically without even looking at these 2 sides. And then No,
It's only internet one,
it's in the grade 10 stuff.
but it's not Euclidean exactly.
Oh yeah. When it comes to these quads, you won't very often see in the grade 12 stuff them asking you to prove that a shape is a certain type of quad.
Like, for example, kites are also they're going to know that.
Yes, yeah. So this is something that, if it has been a problem for you, it's pretty much relegated to the grade 10 stuff, which is one of the reasons that grade 10 geometry is such a problem. But
yeah, the grade 12 work is essentially 3 years of work. It's the whole FET phase.
but if they don't test this, then it's not. Yeah. So this is the thing. So you technically can be tested on it, and you'll find for a lot of internal exams, like I know I've seen a lot of internal exams where they test this type of thing. If they pay attention, they would notice that this stuff is never in the finals. So they are kind of out of step there and not really preparing guys for the finals. That's something good to remember. But you can go through these and memorize them. I'll just put it way down at the bottom of the list of priorities. Once you can do all these proofs, blindfolded, then you can go and look at this stuff. Okay, I think we've got time for like 1 or 2 more. Thank you for the questions, Trinity. I must also mention, sorry guys, about the link. I know that I circulated the document, and then what happened was there was a problem with the first session. So next week's session will be the link that's in the PDF. We will also, just remember, we'll be posting the link, reposting that link on the socials and on the WhatsApp. So, okay, then that is where I think we'll call it a day for today, and we'll pick up on this next week. Cheers, guys.
It's okay.